Hey guys, today we're doing chapter 2.3 of functions. So first we're going to be dealing with even and odd functions. So even and odd functions is basically just another way to think about symmetry in terms of y-axis symmetry and origin symmetry. So how the book writes it is for even, it's f of negative x equals f of x. So what that means is if you plug in a negative value for x, there's also going to be a positive value for x, which is the same as we said earlier for y-axis symmetry. So you're going to have the coordinates x, y, and negative x, y. And then for odd functions, it's going to be the origin symmetry. So it's going to be f of negative x equals negative f of x. So basically, if you plug in a negative value for x, you're also going to get you can get a negative function. So that's the same thing as x, y, and negative x, negative y. So if you remember for origin symmetry, for any point on the function, on the graph, x, y, so if you plug in a value for x and a value for y, that you're also going to have the point negative x and negative y on that graph. So if this is the graph of y equals x squared. So if you have the point, you have this point here, you're also going to have the corresponding point over here. So that's this is xy and this is negative xy. So that's an even function. Basically, it's just y-axis symmetry. And then an odd function like this, which is y equals x cubed. It's a cubic function. For any point on here, if you found this point, xy, if you go negative x and negative y, negative x would take you over here, and negative y would take you down here. So then you're also going to have the corresponding point down here. And so that's an odd function. Another way to think about it is if you're given, if it's an odd function, later on you'll learn specific functions can be odd or even functions. So if you know it's an odd function, it gives you f of negative x, you have the function and it asks you to plug in a specific value of x, you can rewrite it by moving the negative sign out, so negative f of x. So that'll come in handy later. Whereas an even function, if you plug in a negative value for x, you can drop it and just write f of x to make the problem easier. So that'll come later, but that's something to think about. Okay, so now we're actually going to switch subjects a little bit because pre-calculus tends to do that. It doesn't really make much sense in the order. So now we're going to deal with maxima and minima of a function. So if you think of a function can increase. Like here, this function is constantly increasing because this point here is greater than this point here. So you can say it's increasing. This function is decreasing because this point here is greater than this point here, and so on and so forth. It's constant if it's like this, and no point is greater than the next, right? So with that being said, you can find what's called a local maxima, or a local maxima is just the greatest, it's just a point where the function reaches a height and then begins to decrease again. So if you looked at this upside down parabola, this would be the local maxima here. And it would be at point x and y. So you can tell this is a local maximum because the function is increasing, and then it gets to a point where it levels off, and then it begins decreasing. So increasing to decreasing is a max. And now if you go decreasing to increasing, it's a minima. So if you look at an example of that, it would be the same thing like this. This is point x, point y. So you'd say the local minima is at point xy because the function is decreasing and then begins to increase at this point. So it's the point when it switches from decreasing to increasing or increasing to decreasing. You can just identify it on a graph because it looks, you can see it as the highest point. Now we actually have something called an absolute maxima and minima. So an absolute maxima or minima is the highest or lowest point on the entire function within a certain domain. So if you were to have this graph, and your domain, say, went from 0 here to, let's say this is 5. So that's your domain. That's the only x values the function can deal with. So say it goes up like this and then comes over here at 5. So you can see here is a local maxima, here's a local minima, and but your absolute maxima and minima are going to be, this is your absolute maxima and this is going to be your absolute minima, because this point is higher than that one. So this is the absolute because it's the highest point on the entire function within this domain from 0 to 5. And this right here is the lowest because nothing comes as low as that point. So the important thing here is for absolute max or minima, you need to check the endpoints as well. Because here, if you didn't check the endpoints, you would call this one your absolute maxima and this one your absolute minima, but it's actually this and this. So check the endpoints to make sure that check them before you claim a point is an absolute maximum or minima. So then the next thing the book covers is your average rate of change. So you guys all know what slope is. It's your rise over your run, your change in y over your change in x. So there's also something called the average rate of change, or your average slope of a function in a closed domain. So here in this function, you can see that the domain is from -4 to 6. So it's a closed function, it's a closed domain. Your function's all right here. So you can actually find the average slope, because you can see here the slope's going to be changing all throughout this curve, right? Because it's constantly moving and constantly changing direction. So you can actually find the average slope is going to be between the endpoints where it ends up. So if you were to draw a line like that from one endpoint to the other, that is your average rate of change. So you can find that by taking your endpoint coordinates and calculating the slope. So y sub 2 minus y sub 1, 3 minus -2 over 6 minus -4. So then that's going to be 5 over 10, 1/2. So the slope of that line is 1/2, and so we can say the average rate of change for this function in this closed interval, this closed domain, is going to be 1/2. You can also take it from any point. So if it changed the domain, it said, what's the average rate of change between points between -2 and 4? And so you could just find the endpoints, where it is at -2 and where it is at 4, and connect those and find the slope of this line. And so that'll give you the average rate of change from -2 to 4. So you just pick the endpoints and find the slope between those 2 points. The book then defines a term called the secant line. And so the secant line is, you already know what it is, I actually just explained it. It's this line right here, the line that connects the endpoints, your average rate of change line. That's called the secant line. So if you find the slope of the secant line, that's your average rate of change, which is what we already did. However, you just need to know the terminology. So this is the secant line. It's connecting your 2 endpoints of a function. And that's about it for chapter 2.3. It's pretty straightforward, but you're going to get into more complex usages of secant lines and average rate of change and slopes.